Today, as you know, I'm going to present my PhD research, which was titled Dealing with Uncertainties in the Dutch Gas Sector. Simply, that was a policy analysis study for the Dutch gas sector, and by gas here I mean both natural gas and renewable gas used as a fuel, but mainly natural gas, as I refer in the picture. And the presentation is going to be actually quite short and compact. But I will be happy to go deeper into the material in the discussion session afterwards. Natural gas has a long history in the Netherlands, which started in 1959 when they discovered a huge natural gas field in the north of the country. And after this discovery, everything has developed very rapidly, especially the infrastructure was developed very rapidly, and in a very short time natural gas has become the primary energy source. And currently the energy system is dependent on natural gas by 46% or something like that. And in this period, for decades, consumers enjoyed this abundant, cheap and relatively clean energy source. But it's not only consumers, but also the producers and the government made use of pretty good profits out of natural gas. And but that was the past, and there is future. In the future, due to depletion, natural gas resources are expected to decline, but to producers and also the state would like to keep it high. And depending on the depletion, natural gas price is expected to increase, but of course consumers would like low prices. And again, due to depletion, state revenues are going to decline, but so state would like to have high revenues, therefore they would like to have high natural gas production. Not only because of state revenues, but also to secure the supply to the consumers. And actually no one knows what's going to happen to CO2 emissions, but they are desired to be reduced, first down to 1990 levels and maybe to zero later. So these are the future goals, main future goals in the gas and energy system. But by nature, they are conflicting. We cannot get what we want all the time. For example, if we would like to reduce CO2 emissions, that means that we may not be able to increase the natural gas production because it's not a clean source, at least as clean as renewable energy sources. Or we can try to maintain a high natural gas production, but that causes earthquakes in the north of the country due to natural gas extraction and further social controversy that comes with this production activity. So policy goals are conflicting by nature. It's quite difficult to make a decision, but still to reach these goals in a way that all actors and all stakeholders are satisfied, action needed. The government needs to make policy decisions to reach these goals. And the main research question of my research focused on this assessment of decisions, actions, and asked for the effective policy options that are effective in meeting the conflicting interests of the actors in the natural and renewable gas sector, and also policy options that are robust against uncertainties in the long term. And answering this question is, of course, is not easy. It's not straightforward. In the large gas sector or in general for any policy problem, the system that connects these policies to the goals is quite complex due to the interactions between several factors. Therefore, it's not an easy question. However, there is a remedy, often used remedy for this complexity problem, and this is the simulation modeling. Simulation models are used to represent the system of interest and then to generate an estimate of the future, so that and this estimate can be like a time series data, as I show on this picture. And this such estimations can be generated for any policy, then they can be compared to each other, and you select one of the policy options. So that's kind of the conventional way, but there is one more aspect of policy problems that lead to more problems that make the question more difficult to answer, and that aspect is uncertainty. Uncertainty either emerges as an external factor which decision makers cannot control, or it can manifest itself in this system because how the factors are linked to each other is not known, or it can be in the value system of the decision maker, for example, about how they prioritize the policy goals or how they measure the performance. And in the presence of uncertainty, we cannot rely on anymore on a best estimate future that simulation models generate, because there are many possibilities, many scenarios, like I showed in that case. And yeah, we cannot use the conventional approach that I tried to describe earlier. One solution suggested for this is exploratory modeling and analysis approach. I use this approach in my study. I will call it EMA from now on. And in this simplest words, EMA suggests to explore a wide variety of future possibilities rather than a best estimate future, and to base decisions on this variety of scenarios rather than a single best estimate future. So in that case, robustness of policies becomes the important performance measure rather than the measure on the outcome indicators or policy goals. And another core point of EMA approach is the identification of vulnerabilities. Vulnerabilities are the parts of scenario space where the outcomes are most sensitive. And in that case, policy options can be improved further in terms of their robustness. So as I said, I use this approach. And to represent the gas sector, I have developed a system dynamics simulation model. The main purpose of this model was to, again, I'm repeating, but the purpose of the model was to generate scenarios and explore the future. It took almost 3 years, and I'm quite sorry to show it on one picture like that, but for now it had to be in that form, I guess. The model I developed and used in this study mainly included several supply options, being domestically produced natural gas, imported natural gas, or domestically produced renewable gas, and several demand factors at the other side, like demand from the electricity sector or demand from the households, industry, agriculture, etc. And these supply and demand options are balanced through the market mechanisms and the infrastructure constraints. And another core point is actually these supply options compete with each other, and that competition generates the outcome indicators that operationalize the policy goals. For example, demand coverage, to what extent the demand is met, or the percentage of renewable gas in the supply. They develop through following the competition between these supply options. Here I have a list of which actors included in this model, what kind of decisions they make. And mainly natural gas producers. Let me say one more thing beforehand, because the model, I don't know if you have modelers in the room, but the model was more focused on the supply side rather than the demand side, and the supply aspects, supply options were modeled in more detail. And they can be actually individually used for each supply group to look at how they develop, how the supply amounts develop over time, and what kind of decisions can be made or changed in a desired way. what I mean. So for natural gas resources, estimation of natural gas resources, the natural gas component can be used separately, or to understand renewable gas supply chain mechanism, renewable gas part can be used separately. And in general, in this list, you see natural gas producers make decisions, make investment decisions on exploration and production, or the price that they would like to receive. Renewable gas producers make similar decisions, and as well as electricity producers. And system operators, transmission system operators or distribution system operators, they make decisions on the infrastructure capacity. I used this model to generate scenarios, as I said. So for one of the outcome indicators, it generates several scenarios like this. So in this figure, for example, each line represents a scenario generated by a different combination of input elements of the model. And this graph at the right-hand side shows the density of these scenarios. So this figure basically represents a scenario space. And when I would like to compare policies to each other based on such a scenario space, there are some complications. In this figure, this is still for one criterion, for one outcome indicator, and each color represents the policy. And as we see, scenario spaces show different characteristics. If you want to compare them in terms of their robustness, then we have the problem of how this comparison should be, which characteristics should be taken into account, and how the decision should be made, basically. And one more thing, and also where in time we should compare these results, because scenarios are transient. In that case, they are for 50 years. So where in time we should really compare the outcomes. And in addition to this time aspect and uncertainty aspect, we have the multiplicity of criteria, because we don't have a single policy goal, we have many, so we have many of these graphs. So now to address these three issues of decision making about uncertainty, time, and multi-criteria, I've come up with that idea of three-dimensional framework to combine these three aspects. In one aspect, I have the time dimension, where I suggest to look at these scenario spaces either statically at particular points in time, or dynamically, where I compare policies to each other at each point in time. To deal with the multiplicity of policy goals, I suggest to use multi-criteria decision analysis methods. And to deal with the uncertainty aspect, or namely the robustness of policy options to deal with uncertainty, I suggest to use different robustness metrics, which take different characteristics of the scenario space into account. And one thing I need to mention here is the multiplicity of methodological options that I use for each of these dimensions, because the idea is that we can select a method to carry out such an analysis, but we don't know that it's the best method to do this, and the results may be highly dependent on the method we chose. Actually, there is a methodological uncertainty there as well. That's why for each of these dimensions, I prefer to use several options and conduct the analysis with a combination of each. And so using the scenario space generated by the model and this framework, I compared several policies to each other. In total, there are 9, I think, but I wanted to name a few here, like the limiting natural gas production, or subsidization of renewable gas, or having communicative policies with the industry for renewable gas production, or permission to shale gas production. And the others include things about tax or that kind of things. And one thing that I need to mention is that these policies are static, and I look at the static robustness of policies. They are not adapted over time, they are not changed, they are implemented at one point in time, and the results are observed over time after this implementation. And since I used many methodological options, the results are also many. I'm not going to explain this, but I just wanted to prove that I have done something. This is for static time metrics, where I look at for particular time metrics. Each side represents a ranking of the policy options or a Pareto set. And the results for some robustness metrics, they are similar, or for some time metrics, they are similar, they vary over time. They are dependent on the method chosen. And further, I have analyzed this table to see if there are repeated occurrences. And also, as I said, I compared these policies dynamically over time. For example, like that one. Here the x-axis is time, y-axis shows the policy options, and each color represents, each color corresponds to one of the robustness metrics. And again, what I can say in general is that results are dependent on the robustness metric. The most preferred policy is dependent on the robustness metric, or they are scattered over time, so the most preferred policy changes over time. But despite this variation, some of the policies perform well persistently over time and with many of the robustness metrics. From here, I jump to my conclusions. The first conclusion is that yes, the results are highly method dependent. They are dependent on the robustness metric chosen or the multi-criteria method used. But still, some of the policy options, as I said, perform well repeatedly with many of these methodological options. In the short term, subsidization policy and business as usual policy perform well compared to the others, and this means that for short-term decision makers, they look like favorable options. In the mid-term, subsidization is still a good policy, but this time communicative policies about renewable gas production perform better, and it's more or less the same in the even longer term, for example after 2050. But in this period also shale gas production emerges as a favorable policy. And these policies, especially the subsidization policy, which I looked in more detail actually, is most vulnerable to producer behavior. If producers, not the decision makers, but producers make long-term or have a long-term or short-term view in their decision making, and again the policies are most vulnerable to market mechanisms, and that's why communicative policies can deal with these vulnerabilities better. Another conclusion, methodology conclusion, is that it's valuable to use multiple methodological options and especially multiple robustness metrics, because some of them can lead to mistakes and misunderstandings. I have some examples of it, which I will not go into detail now. That's why it's important, but still there is no need to use as many metrics as I used in my study, because I was able to show some of them are redundant and cover each other. The second conclusion is about the shortcoming of this framework that I presented to you. Because the information resulting from this framework is quite compact and it's not really transparent. After some analysis, it shows which policies are more favorable, which ones are not. So this is not really transparent. So it tells you what to do, but not why. And answering the why question requires further analysis which I did partially in my study. But this shortcoming actually shows a trade-off between providing a quantitative and comprehensive analysis and the transparency and understandability of the results. In future research, I say this dynamic comparison of policies can be used in dynamic adaptive policy design. And also I use very preliminary multi-criteria methods. More multi-criteria methods can be used. And as I said, the model was more focused on the supply side, as this is a common view in the energy modeling area. Demand side of the model can be paid more attention. Thank you very much for listening. I think I managed it in 20 minutes. And thanks again, and if you have questions.
Thanks very much, Sibel. It's very interesting talk. I have one general question and a couple of details later after the others. With regards to the general question, you showed that actually what you, I mean, it is sensitive to the MCDA method that you use. I know you'll be using others, and to the robustness criteria. But if you are developing, for example, this as a decision support tool to policymakers, at the end they want to make a decision based on something. So would you at the end, when you do all this evaluation, sort of find out which is the sort of best MCDA method or best robustness matrix for this example? Because if you have a lot of variation, I'm not sure what the policymakers, how would they use this information to make their decision?
Yeah. I understand the question. That's why I try to filter this information and show a small table at the end with the good policy options. But I think if that is to be used for a decision support tool, decision maker should have the option to select which methods he or she wants to use, because my study did not aim to compare different MCDA methods, and I think even if we dare to do so, I don't think that we could reach a conclusion about which one is the best, because they depend on certain preferences. And I think in a decision support tool, the options would be available, and what they mean and the implications would be available, and the decision maker can make the choice. The same goes for the robustness metrics, because they define, they refer to different characteristics. For example, like the risk proneness or risk aversion. If someone prefers a low average value but a very narrow variation, very little narrow variation, then they should go for one of the metrics. But if they take more risk, if they are willing to take more risk, they can go for options that value that are focused on the value rather than the variation.
Okay, thank you.
Thanks.
I mean, you said in your last words in your presentation that you have to make a decision between kind of being very much on the explaining side versus being comprehensive. But you did suggest some policies and you did recommend them. To what extent does your analysis allow you to tell us why you recommend them? What is the underlying mechanisms why they came out first? And also different ones under different time horizons.
Yeah, I haven't put slides about this, but there is something called scenario discovery that I conducted that helps to find why these differences occur based on the uncertainties. For example, here you see some switches between the most preferred policy options at particular
Could you
point.
explain how to read that?
X-axis is the time from 2010 here, from 2010 to 60, and Y-axis is the policies, and each dot dots represent the most preferred policies, and the color represent the robustness metric. So if I use, for example, mean divided by standard deviation as a robustness metric, at the beginning, in the few years, we see business as usual policy is the most preferred policy. It's green here. But then later, over time, persistently, subsidization policy is the most preferred policy. At the end of the time horizon, for around 10 years, less than 10 years, this time renewables obligation policy, which was another option that I didn't mention, is the most preferred one. So here we have these jumps at particular points, and if we want to understand why this occurs, why this changes suddenly, and because this is based on robustness, not only the performance on, for example, demand coverage or price, but also on robustness. So therefore, which uncertainties are important in the final behavior is something that I had to figure out. That's why I used this scenario discovery mechanism that showed me that I mentioned here. This market mechanism and producer behavior are the vulnerabilities of these policies. Here, I go back again, that's being a bit confusing. For example, this subsidization policy suddenly changes to be the biomethane goal, the most preferred one. And this is because producers, when they receive subsidies from the government, if they have a short-term view and if they do not consider their gains in the long term, then biomethane goal policy is a better one. But if they consider their long-term gains, then subsidization policy is a better one. So it gives that kind of insights about the higher performance of a policy option compared to another one. But that I can tell to you later. But it doesn't, in the system dynamics sense, it doesn't look at the dynamics over time, but it rather finds the parameters and external factors or model structures that lead to this behavior.
Mm-hmm. But for each of them, you could have like the underlying causal explanation why one policy does not work well in the short term, but why it works well in the long term.
That I do based on my interaction with the model as the modeler, not by showing the results. Yeah. It can be done in that way, but it requires further analysis. Yeah. Thanks. Yes.
Yeah, just to follow up on Mickey's question, did you try or think of trying simplifying the model that you built significantly to increase the transparency and make it more understandable, and then checking to see if with this simplified model you get different or similar results in terms of policy recommendation? Did you?
I wanted to do this, but there was no time. That's why I didn't. But I think a simpler model could help to deal with this transparency issue, but it wouldn't really help in the sense that, let me put it like that, even if the model is simpler, you can generate more analysis by looking at single scenarios, looking at a limited number of scenarios so that people can understand. But here I'm talking about thousands of scenarios and a robustness value determined based on these thousands of scenarios. That's why even if the model is smaller, it could help, but the resulting outcome still would be that kind of does. It's more about the analysis required to deal with uncertainty and multi-criteria rather than the model itself. Thanks.
I have a quick question just based on that graph. So from what I understand from my non-system dynamics background, so a person or a decision maker would select the most suitable combination of policies based on selecting one of the robustness metrics and see where that's mapped across the scenarios. Does the uncertainty take into account what would happen when you would transfer between the different scenarios along the time kind of period covered?
No. If I understood you correctly, I haven't taken this into account because the policies are implemented at one particular point in time. That's the beginning. So we make decisions now and we see how it goes over time. That's why it doesn't include the switches between the policies, like if they are implemented in a varying or adaptable way. Thanks.
This another question. You talked about uncertainties in terms of sort of simulating deterministic scenarios. An alternative approach would you put it in a stochastic framework. Now, why have you opted for the sort of a deterministic framework rather than a stochastic framework?
It's because we don't know all these probabilities that we could use in a stochastic approach, because it comes from the idea of deep uncertainty, where alternatives, possibilities can be listed, but they cannot be ordered, or probability functions cannot be assigned to these uncertainties. And for the policy problems, most of the case, these uncertainties fall to the deep uncertainty category. Even if we try our best, probability functions are based on strong assumptions. So that's why here I just look at scenarios that represent different options rather than having a probability attached to it.
Okay, thank you.
I wanted to ask about the policies. What are the regret policies?
Regret is not policy, but it's a robustness metric. It's a way to define robustness. So it goes like, so you look at each scenario separately, and for each scenario you find the best policy option. That's the best one in that scenario. Then you compare. Then you find the policy options that minimizes the. Then there's maximum regret in between. Maximum regret is the for each. How can I explain this in a simple way? You find the best one for each scenario, and then you look at the regret of each policy option in each scenario from this best policy option. That means that, so I make a decision, I choose policy A, but policy B is the best one. And if this scenario occurs, the difference between policy A and policy B will be my regret, because maybe I'm going to lose some money. It's going to be the regret amount. Then then it finds the maximum regret over all these scenarios and chooses the policy option with the minimum maximum regret. That, okay, yeah, I was going to go continue.
Yeah. And which one that is like the behavior as usual, right? So I find that that's the last one, is behavior as usual, right? So that is the one that minimizes the regret. So
no, actually the one that minimizes regret is shale gas. That's why I was interested. It's more shale.
No, shale gas, with this minimization of maximum regret, at the end it's shale gas for a while, but also the biomethane goal. The gray one, regret threshold, is slightly different than this maximum regret one, because it doesn't minimize this maximum distance from the best policy, but it rather looks at policies that push many scenarios around the zero regret option. So it's not a certain, it's not a definite absolute measure, but it's rather about the density of scenarios around the zero regret option, around the best option that I can get.
Okay, it's quite striking that that is the behavior as usual. So
yeah,
that means kind of with what we are doing at the moment,
you can go on with it if you look at that one.
It still means kind of in a way we minimize our risk in many ways, right?
Yes, that's true. That's true. I agree.
So-
Yeah, how old are you, please?
So do you understand correctly that this is from the perspective of the policymaker?
Yes.
And then could you also look at the kind of the preferred options for the stakeholders?
I did something like that because here I say there are different multi-criteria options, and I look at one option that that assigns different weights to the policy goals, and actually stakeholders can be represented with different sets, like how differently they prioritize different policy goals. So with this, when I use this method, I use different weight combinations for the assessment. Again, a variety of weights assigned to each option, and then that showed how robust the policy is to the weights of the policy goal. So it doesn't look at each stakeholder separately. So it doesn't say, for example, this is what industry wants, this is what consumer wants, but it looks at the policy options that are robust against different prioritizations of this policy goal. So stakeholders are taken into account implicitly, not explicitly. Thanks.
Yeah, related with that, can we go back to the other graph?
The most popular one.
Yeah, the most popular one, because it has colors inside. Is it? Do you think it is fair? It would be fair to say that you can assign each of those criteria on the right-hand side. You can assign each of those to one or more stakeholders. Like, say, for instance, that consumers normally use regret thresholds, or
Maybe it can be done, but it definitely requires further research. It requires going to people and asking things like, how do you value uncertainty, or what is most important for you when you make decisions under uncertainty.
Mhm.
So then maybe as a result of that kind of research you can find this is the mindset of consumers, so they can be attached to this regret criterion, regret metric, or another group can be attached to another one. But in general, without further research, we cannot say such a thing. I cannot say such a thing, because they rather represent different valuations. Even in the same stakeholder group, one person can choose one of the metrics, the other can choose the other of the metrics.
so they were chosen mostly based on their like statistical or scientific value, and not because they relate to necessarily to something in the real world.
Yes, they are the metrics commonly used in the literature for decision making under uncertainty, or that some of them are not necessarily used for this purpose, but I thought they can be used and I brought them in. Thanks.
One question. If you chose one robust, I mean, not in the slides you showed, but I'm interested to know that if you used one robust measure and you compared, let's say, the lexicographic method to the Pareto optimal you had, how did you try comparing them across one set of robustness?
Because then also when I use the dynamic method, it becomes more complicated. But here, for one robustness metric, so these are the results of Pareto and these are the results of lexicographic. And Pareto set, in my case, was not really informative because I have 8 criteria and 9 policy options. So with 8 criteria, Pareto set is usually the entire set of policy options, so it wasn't much informative. But this is the way to compare them and see.
Okay.
Thank you. Any other questions? Then thank you very much
Thank you
for
very much.
listening. Have a